Hello everyone, we're going to go through another example now. The example we have here, we're again going to find the complexity of a recurrence relation. We're going to solve this by using the substitution method. So we look at the right hand side of our recurrence and identify what is inside of t of n. Here we have t of n minus 5, so we're going to plug n minus 5 back into t. So we have to plug n minus 5 into our equation. Maybe we even give it a name. Let's just designate it with like a color here, purple line. Doing that, we have t of n minus 5 on the right hand side is equal to t of n minus 5 minus 5, which is n minus 10. And then we have plus c times radical n minus 5, replacing all copies of n with n minus 5. We're then going to substitute that back into the original recurrence relation. So we get t of n is equal to substituting the red underlined part for t of n minus 5. We have t of n minus 10 plus c times radical n minus 5. That's doing the first part of the substitution. Then we need to be careful because we still have that c radical n over there. So it's plus c times radical n. We need to make another substitution with whatever is now appearing inside of our t. So now we should plug in n minus 10 into our purple equation. So we get t of n minus 10 is equal to t of n minus 10 minus 5, which is n minus 15, plus c times radical n minus 10. We're going to substitute the blue underlined bit for t of n minus 10. Doing so, we get t of n is equal to t of n minus 15 plus c times radical n minus 10. That's from the substitution, but then we still have those two additional terms, plus c radical n minus 5 plus c radical n. Once we've arrived at this expression, our goal is to identify a pattern in what we see here. There are two places we need to identify the pattern. First, we need to identify the pattern for t of n minus 15 and t of n minus 10 and t of n minus 5. That looks like stuff like t of n minus 5 times k. That one's usually not too bad. The other part is all of these other terms, c times radical n minus 10 plus c times radical n minus 5 plus c times radical n. In the previous one, we have one fewer term, and the one before that, one fewer term again. This always, like we've seen in the past, we can write as a summation from I equals 0 to k minus 1, yk minus 1. The largest term we're going to be plugging into these radicals we're seeing appearing is 1 less than the thing that is appearing inside of t. We have n minus 10 when we have n minus 15 inside of t. We had n minus 5 when we had n minus 10 inside of t. So what appears inside of the summation, well, it's some constant times n minus 5 times I. You need to be careful to make sure you put an I there because we need to add up all of the different multiples of 5 there. So here we have an expression. So for any value of k, I have that right hand side. For any value of k, I have that t of n equals t of n minus 5 times k plus the summation from I equals 0 to k minus 1 of c times radical n minus 5 times I. So we have our new generic expression here, and now we need to try and implement our base case. To have that happen, we need to take whatever is inside of t and set it equal to our base case. So this stops when whatever is appearing inside of t, n minus 5 times k, is equal to our base case, which if we scroll up might be we have t of 0 equals c, so we want to set this equal to 0 and solve that for k. So we have k equals n over 5, add by 5k and divide by 5. We then substitute that into our expression there. So we have that, let's do it in purple, t of n equals t of 0. I know n minus 5k is equal to 0, so I don't need to do any math there, plus the summation from I equals 0 to k minus 1 of c times radical n minus 5I. As we've seen in the past, now we've reduced the problem to one of analyzing a summation, which we have plenty of skill at. This one we have to bound. There is no way around that. So we're going to analyze that summation. Let's bound it above. Bound above. To bound that summation from above, we're going to take the original summation from I equals 1 to k minus 1 of radical n minus 5I. We replace each term in the summation with the largest term. The largest term in that summation is radical n. Why is it the largest? Well, n minus 5I is decreasing in I, so the value of I that would make it the largest would be the smallest value of I I'm considering. So it should be plugging in I equals 0, which would be radical n. By doing so, we now have a fixed thing. We are adding up a fixed number of times. So how many times? Well, that's going to be the top minus the bottom plus 1 times whatever was inside of the summation, in this case radical n. There's very little way to proceed here without plugging in k, so let's plug in k, which is equal to n over 5 times radical n, and now hopefully it's clear that that should be in big O of n to the 3/2. So that's the bound above. That's usually pretty straightforward. Let's also bound it below. So bound below. To bound it from below, we take the original summation from I equals 0 to k minus 1 of radical n minus 5 times I. We make it smaller in two ways. Step 1, we cut out half of the terms. When I cut out half of the terms here, I'm actually going to go from I equals 0 to k over 2 minus 1. Why do I do that? Later in the problem, we'll see that that lets me get rid of a constant, and that'll be convenient. Now we need to plug in a value of I. I need to plug in a value of I to make it smaller. Again, it's decreasing in I, so larger values make it smaller. A convenient value of I that is guaranteed larger than or equal to every single term inside of this summation would be k over 2. So I replace I with k over 2. That would definitely make it smaller because that's plugging in a large value of I. I now have, by doing that, by plugging in the value of I am now adding up a fixed thing a fixed number of times. Well, how many times? Just like before, we have top minus bottom plus 1 times radical n minus 5/2 k. Notice that me going to k over 2 minus 1 got rid of a constant out front for me that I would have had to pay attention to otherwise. So k over 2, I don't really see much way to get around plugging in k. But thankfully I know what k is. K is n over 5. So I have n over 5 over 2, which is n over 10, times radical n minus 5/2. Plug in k again, which is again n over 5. Some nice math happens here. We have 5 and 5 cancel. So we have n minus n over 2 inside of the square root. And hey, that's n over 2, so that's convenient. Equals n over 2 times radical n over 2. And at this point, maybe you say, I can recognize that that is in big omega of n to the 3/2. So from the part in blue here, we have that it's in big omega of n to the 3/2. From the part in red here, we have that it's in big O of n to the 3/2. So the entire summation must be in theta of n to the 3/2. So the original summation from I equals 0 to k minus 1 of radical n minus 5 times I must be in theta of n to the 3 halves. With that in mind, we can now take the summation that appears in our recurrence relation up here and substitute in theta n to the 3 halves. So thus the summation, nope, don't let me lie to you, t of n is equal to c. Why do we have a c there? Let's scroll up. Well, it was t of 0, and t of 0 conveniently is just c. Oops, let's make this green. I apologize. I'm going to redo that. We're going to have t of n is equal to c plus c times the summation, which the summation we're now substituting in theta n to the 3 halves. At this point, maybe you go, that's clearly in theta of n to the 3 halves, so therefore t of n is in theta n to the 3 halves. Notice that for this problem, it was similar to some of those we've worked on in the past, and bounding was actually the only way that we could proceed on this problem. There was no way around it because the summation that we had a square root in it, and we've noticed before there is no way around having to bound those things. So for a problem like this, there is no way we can get around having to bound it. But otherwise, this is extremely similar to all the problems we've analyzed in the past. We needed to make substitutions. After we make the substitutions, we identify a pattern, and then we eventually get to a summation that we can analyze. And then eventually we can determine the complexity.